It's January, so I'm a little cold, but fortunately, my good friends at Solomon Schechter hooked me up with this Mathcounts sweatshirt. Now, you know, it's a new Mathcounts sweatshirt because it's even got the new Mathcounts logo. So I'm going to stay warm while we work on some analytic geometry here. Now, that analytic means algebra. We're going to mix in some algebra with our geometry. Now, on this first problem, at the point xx is equidistant, that means same distance, from -2, 5, and from 3, -2. That distance in there tells us we're going to use the distance formula. You remember that? Difference in the x-coordinates squared plus the difference in the y-coordinates squared equals the square of the distance between the 2 points. Well, that means that the distance formula is just algebra speak for the Pythagorean theorem. Let's put it to work. And our difference in x-coordinates, we'll square that, plus the square of the difference in the y-coordinates. Take the square root of that mess, and that gives us the distance between these 2 points. Now, the distance between these 2 points, we just use the distance formula again. Square of x minus 3 plus the square of the difference in the y-coordinates. And we have a big mess. Now, we could go ahead and start squaring things and squaring things and squaring things and squaring things, and eventually we'll get the answer. When we look at these equations, think about the equation before you start bashing away. We see Mathcounts made life a little bit easy for us by making these 2 pieces of these equations the same. Now that tells us that this whole mess equals this whole mess when these 2 pieces in here are equal, because these 2 pieces out here are already equal. So this mess equals this mess when x minus 5, when the square of x minus 5 equals the square of x minus 3. Now we could square these out and do some algebra, but well, the squares of 2 numbers are equal only when either the numbers are equal or their opposites are equal. And clearly x minus 5 and x minus 3 can't be equal. They're 2 apart, so they must be opposites, and we can tell just by looking at it that x minus 5 and x minus 3 are opposites when x is 4, and we have the answer to our problem. Now, what would we have done if these 2 hadn't been so conveniently the same? I'll let you think about that later, because that gets into some pretty nasty algebra, and I don't like some nasty algebra. Let's try another problem. Doesn't look like Mathcounts made this one easy on us. Well, you know, when I get a complicated problem like this, complicated analytic geometry problem, start with a picture. Get a better feel for the problem. Go ahead and put all our points on here. A is at 3, 1. B's up here at 2, 4. A prime is out here at 4, 2. And B prime is out here somewhere, 7, 3. And the center of rotation, we have no idea where it is. We'll call it xy. Now, we've got some geometry here. We have a picture. But, well, we'd like to get some algebra out of this. We'd like to build an equation, or a couple of equations for x and y so we can solve for x and y. Well, an equation means we need to find some things that are equal, but we don't see anything that's equal here. We haven't used the fact that we're dealing with the rotation. Now, where does rotation give us equal things? Let's think about a rotation. Just say, my thumb here, we'll call that the center of rotation. Here's one of the points out there. Now, when we rotate, well, we're keeping the distances between these points out here and the center of rotation the same. Start here, we rotate. This distance is the same as this distance. So our center of rotation, xy, has to be the same distance from A and A prime. Wherever xy is, we're rotating, and A goes to A prime. So the distance from the center of rotation to A is the same as the distance from the center of rotation to A prime. That gives us an equation. Distance between the center of rotation, xy, and 3, 1. Well, we take the difference in x-coordinates squared plus difference in y-coordinates squared, and we know that that distance equals the distance between the center of rotation and A prime. And now we have an equation. it's just not a very nice equation. Now we could work with this. So we could start squaring and squaring and squaring, and eventually it'll work. But before we start doing that, I'm going to use one of my key analytic geometry strategies. Now, I see an analytic geometry problem, I turn it into algebra, and if the algebra is a mess, I go back to the geometry. And I hope the geometry can give me a better equation. This isn't just an algebra problem, it is also a geometry problem. Can't forget that. So let's go back and look at this again as a geometry problem and see if we can come up with some better algebra. So again, we'll start with our sketch. We've got A prime. I'm not going to put all the coordinates in. I want to keep my diagram a little bit clean. We've got all the coordinates up there anyway. So we're going to go out to 7, 3. Up there. All right, those are our points. Now, the center of rotation we know is equidistant from A and A prime. Now, geometrically speaking, what does equidistant mean? It means that the center of rotation is on the perpendicular bisector of AA prime. That's what we mean geometrically when we say the center of rotation is equidistant from these 2 points. It sits on the perpendicular bisector of the segment AA prime. That means we know a line that the center of rotation is on, and equations for lines are way better than the distance formula. So let's find the equation for that line. We know that line goes through the midpoint of AA prime, so we take the average of the x-coordinates and the average of the y-coordinates to find that midpoint. We know that it sits on this line. So, well, we have one point on the line. We can also find the slope of this line because we know the slope of AA prime. The slope of AA prime, we take the difference in the y-coordinates. 1 minus 2 is negative 1. Divide by the difference in the x-coordinates. 3 minus 4 is negative 1 as well. So the slope of AA prime is 1. That tells us the slope of our perpendicular bisector is negative 1 because 2 lines are perpendicular and our slopes multiplied negative 1. So the slope of this perpendicular bisector, which I'm going to go ahead and sketch in, this slope is negative 1. All right? So now we can write an equation for the perpendicular bisector of AA prime. We know that the slope is negative 1, and that equals the slope we're going to call the center of rotation. We're still calling that xy. Xy sits somewhere on this line. So we know that the slope between xy and 3.5, 1.5, has to be negative 1. It sits on this line. And that slope is going to be difference of our y-coordinates divided by the difference in our x-coordinates. Now we can clean this up. We'll multiply both sides by the x minus 3.5 there. We'll get minus x plus 3.5 equals y minus 1.5. Add x to both sides, add 1.5 to both sides, and we get an equation that is way prettier than that distance formula mess we had before. Now later on, I want you to go back and smash your way through that distance formula mess. You should get an equation that looks a little bit like this. It'll just take you a lot longer to get there. So now that we've taken care of AA prime, we move on to BB prime. And we can use kind of the same thinking that we just did to get an equation, to get another equation for that line. So first we find the midpoint of BB prime. Average of the x-coordinates is 4.5. Average of the y-coordinates is 3.5. And we know that the center of rotation is going to be on the perpendicular bisector of BB prime, which is going to look something like this. And now all we have to do is find the slope of this line because we have one point that is on the line. Well, we have to find the slope of BB prime. Difference in the y-coordinates, 4 minus 3 is 1, divided by the difference in the x-coordinates, 2 minus 7 is negative 5. So the slope of BB prime is negative 1/5, which means that the slope of our perpendicular bisector is 5. So now I can write an equation for this line. I know that xy, the center of rotation, is somewhere on this line. In fact, it has to be on this line, it has to be on this line, it has to be right here. So if you drew a really, really precise diagram, you'd at least have a guess. And we also have a way to check our answer at the end, see if it's kind of close to wherever that point is. Looks like it's just below A prime and just to the right of A. So we might guess that the coordinates are somewhere around 4, 1. That'll give us a check. But let's go ahead and do the algebra. We know that xy sits on this line. So our perpendicular bisector of B prime, we have 5. The slope of this line is the difference of the y-coordinates. We know xy is on this line. Difference of the y-coordinates divided by the difference in the x-coordinates. And again, we clean this up, multiply both sides by x minus 4.5. We get 5x minus 5 times 4.5. 5 times 4 is 20. 5 times 0.5 is 2.5. 22.5 equals y minus 3.5. Again, we'll tidy this up a little bit more. Subtract y from both sides. Add 22.5 to both sides. We'll get 5x minus y equals 19. Now I've got two equations for x and y, and they're really simple equations. We can just add these two equations, and that wipes out y. We add these two equations, we'll get 6x equals 5 plus 19 is 24. And that tells us that x is 4. Put it in this equation, we get y is 1. And sure enough, our answer is 4, 1. And once again, I'd like to remind you the key strategy we used here in this analytic geometry problem was once we saw all this nasty algebra here, we remembered analytic geometry problem. This is also still a geometry problem.